Hi everyone, I am Dr. B. Ravi Kumar, Associate Professor, Department of AC, Institute of Aeronautical Engineering. Today I am going to explain about diode equivalent circuit and load line analysis. Generally, any equivalent circuit can be defined from a combination of elements which are best approximated to analyze the circuit. In this case, diode equivalent circuit. The diode equivalent circuit, an equivalent circuit of a device, is best approximately represented by passive elements like resistor, inductor, capacitor, and a barrier voltage. Why we need this equivalent circuit? In order to analyze any circuit or network in which nonlinear devices like diode and transistors are placed, then it is somewhat difficult to analyze with direct nonlinear devices. In order to analyze the network, replace that nonlinear devices like diode and transistors with suitable elements, resistors, inductors, and capacitors, and the barrier voltage. So, in order to replace this nonlinear device with those elements, so that we can easily analyze those electronic circuits. For example, if you want to analyze a Thevenin's equivalent circuit, Norton circuit, or any electronic circuits which having a voltage, resistors, and diodes. So by replacing this nonlinear device with the equivalent circuit, so that we can analyze with a simple equations, so that we can apply network analysis with Kirchhoff voltage law, Kirchhoff current law, like that. Okay. Now, in order to analyze the nonlinear device, so we can choose some models. Here, there are three different kinds of models to represent a nonlinear device called diode, which are ideal diode and a second approximation of diode, which is also called a piecewise linear, and the third approximation, which is also called practical diode. So by using these three models, we can analyze the nonlinear diode. First, coming to the first model, we can explain this first model of diode by taking some approximation values. For an ideal diode, V gamma is equal to 0 and reverse resistance is equal to infinite and forward resistance is equal to 0, as shown in the figure. This one. If you take this, it is a diode VI characteristics. It is in the diode voltage. It is a voltage versus current, diode current. As in case of the ideal diode, there will be no barrier potential whenever taking the PN junction diode. So immediately after giving the biasing, whether it is forward bias or reverse bias, the charge carriers moving from one side to the other side without provided with the barrier voltage. We know that. So in that case, the characteristic graph for PN junction diode is a graph with in reverse bias, the horizontal line which represents the zero current, and a vertical line which represents with the current, straight line current without barrier voltage. So here it is V comma 0 is equal to 0 represents the the barrier voltage is equal to 0. If you see this p-n junction diode, this is the barrier, this is p-type, this is n-type. This is a two-terminal device. So ideally, there will be no any potential across the junction. So without this barrier potential, then directly the majority charge carriers of electrons move towards the n side or p side, and the majority charge carriers of holes move from p side to n side. So in this case, the ideal diode act as a short circuit in forward bias and act as an open circuit in the reverse bias region. That can be seen, we can here in this figure in forward bias, how diode act as a short circuit. So this diode act as a short circuit for ideal diode. So whenever we are giving forward voltage, forward bias connection, the current flow in the p-n junction diode from P to N. When current flow in the p-n junction diode, if it is ideal, so the entire this circuit will be closed loop. So this closed loop circuit can be represented with a short circuit. Diode replaced with a short circuit in forward bias. Whereas in case of reverse bias, we are providing with a reverse voltage. Providing with a reverse voltage. A negative potential is given to the p-type and positive potential of the battery is given to the n-type. Then it is said to be reverse bias. In this reverse bias, whatever whatever the junction earlier, for example, ideally this is the line, no junction will be there. So by giving this reverse voltage, so this junction width will be increases. This goes on increases by increasing the reverse voltage. Whenever reverse voltage increases, it will act as an open circuit. So there is no majority charge carriers current flow in p-n junction diode, only minority charge carriers. But in this case, ideally, no minority charge carriers. We can be considered as these minority currents is ideally 0. So that's why in this case, this diode act as a open circuit. This kind of approximation, this kind of approximation model used for an ideal diode. So simply we can say that for an ideal diode, the barrier potential or barrier voltage is equal to 0, and a reverse resistance RR is equal to infinite, and forward resistance is equal to 0. So we know that this what is the resistance is nothing but one reciprocal of slope. So we know that what is slope, nothing but in this VI graph, delta di by dV. A small any change in the current. For example, you take 2 points. If you take any 2 points in the current, which is represented with delta I or di, and what is the corresponding voltage change here? So that the voltage change will be 0. So a significant change in di divided by 0 volts. So that total slope will be infinite. When slope will be infinite, what is the resistance? So resistance, forward resistance RF is equal to 1 by slope. So 1 by slope nothing but 1 by infinity, which is equal to 0. Similarly, what is the slope here in this reverse bias characteristic? If you take 1 by slope will be 0. So when 1 by slope slope will be 0. 1 by slope will be 0. That will be infinite. So for an ideal diode, three major important elements approximated values are junction barrier voltage is equal to 0, and forward resistance is infinite, and reverse resistance is 0, and reverse resistance is infinite. Coming to the second approximation. In this approximation, just we consider the barrier voltage. In this case, what are the approximated values for a diode is a barrier potential V comma is equal to 0.7, and reverse resistance is equal to infinite, and forward resistance is equal to 0. What is the difference between the previous graph and the present graph of VI characteristics of diode is? So we have a diode with a barrier potential. Here we can consider a significant barrier potential which is available across the junction of a p-n junction diode, which is approximately equal to 0.7 for silicon and 0.3 for germanium. Let us see that when we take that barrier potential in the p-n junction diode, then the current flow in the p-n junction diode up to that barrier potential will be 0. Even from the negative axis, the current flow in the p-n junction diode is 0, which shows a 0 current continues to until the barrier potential of a particular p-n junction diode. After barrier potential, it shows some rising in the current flow, which represents the straight line. In these steps, what happened? Take the p-n junction diode, anode and cathode. This diode can be replaced with the equivalent circuit by using this approximation model, the second approximation model. In this model, if you take a p-n junction diode with a barrier voltage, negative on P side, positive on N side. It is just like a barrier or bridge for a water flows. If you take any bridge, so in that bridge, at bridge, so that it stop the flowing of the water. So whenever the water flow can reach the height of greater than the height of the bridge, then they can mount under, they can flow the water. So until that time, the water stopped at the bridge. So here also, when we can apply a forward bias connection, positive is given to the P side and negative is given to the N side, to the p-n junction diode. Until unless the potential is given to the p-n junction diode, which is called forward bias, which reaches to a potential available across the junction approximately equal to 0.7 for silicon and 0.3 for germanium. So let us consider this VI graph is for silicon. So whenever this forward voltage is rising from 0, 0.1, 0.2, 0.3 until 0.7, so these majority carriers cannot cross the junction and which leads to current flow in the p junction diode. So up to 0.7 there will be no current flow in the p junction diode, which represents the graph is like this straight horizontal line on the x-axis. Once reaching to the cut-in voltage, which is approximately equal to 0.7, then a significant current flow in the p junction diode, so that the current will start and the graph will gets rise. Now see that what is the equivalent circuit diagram for p junction diode in this second approximation of the diode model. So this diode can be equivalent into a simple battery plus minus between anode and cathode. It does not mean that it is a voltage source, so diode acts as a source. It doesn't mean that. So when we modeled this diode in the network analysis, we can consider the diode with a cut-in voltage or barrier voltage which is equal to 0.7 for this approximation, so that we can apply this model. So that resultant circuit, for example, this is a potential given to the ideal diode with a barrier potential is 0.7. Before modeling this diode, the circuit is like this. It is a potential V. So after applying the model equivalent diagram, then the resultant diagram will be .7. So in between, if you want to, if for example there will be a resistor in the network, so now we can find out what is the current flow in the network and what is the voltage across the resistor. We can find out in this way. Otherwise, only by taking simple this expression, this diagram, by taking the nonlinear device diode, so we cannot apply KVL because the current flow in the p junction diode according to mathematical analysis, so it is like a relation between diode current and diode voltage with the exponential term. It is somewhat difficult to analyze this mathematical equation in the network. So in order to replace this diode with the equivalent second approximation with the barrier voltage 0.7, so that we can apply a Kirchhoff voltage law, so that we can find out the current flowing inside the circuit or some voltage across of each element. What happens when reverse bias? So in this case, same way, when we apply the reverse voltage here, here also minus is given to the p type and plus is given to the n type. So this barrier will be extended further, so that it will act as an open circuit even in the reverse bias. So the representation of this diode in this model is like an open circuit. So what is the best approximation for this case in reverse bias? Same network, reverse bias diode. In this approximation, simply we can say that it will act as an open circuit, potential, resistor, act as an open circuit, so that the current flow in the network will be 0. So by taking this model, we can analyze that inside the circuit the current flow will be 0. And then last approximation, which is called piecewise linear approximation or practical diode model approximation. In this practical diode model approximation or piecewise linear approximation, So the cut-in voltage, consider the barrier voltage or cut-in voltage V gamma is equal to 0.7, and diode reverse resistance RR less than infinite, typically some several mega ohms, and RF forward resistance of the diode, which is equal to some small RD, typically some less than 50 ohms, as shown in the figure. Again, we can consider the P junction diode VI characteristics, diode voltage, diode current. Now, what are the assumptions have taken in this model? First assumption is take the barrier, consider the barrier voltage V gamma, so that graph shifted from first approximation to from this point to V gamma point. That is the first assumption, first approximation. And second one is taken from the second graph. This straight line, which represents that there will be no slope in the graph, which can be represented that diode has forward resistance is equal to 0. Whenever there is a resistance which represents the slope of that curve, slope of the curve for that device. So in the second case, so we didn't take any resistance, forward resistance. So the slope of that curve will be 0. It is a straight line, infinite, which is equal to RF is equal to 0. Now consider that in this third case, piecewise linear, assume that some current flow in the P junction diode, so and also there will be some resistance available in the P junction diode. This resistance can be approximately represented with the slope of this curve. So the slope of this curve represents the resistance, significant resistance existed in the P junction diode. What happened in this case? So first we will consider forward bias. So in this forward bias, by taking this, considering this barrier voltage,
అన్ని బంద్ చేసి వెళ్ళండి.
yes sir.
ఓకేనా?
Sure.
బంద్ చేసి ఏసీ కూడా బంద్ చేసి.
Okay. So in the forward bias up to this barrier voltage, so V gamma, up to this V gamma, there will be no current flow in the P junction diode. So once this V gamma greater than V gamma, then a significant current flow in the P junction diode. But in the third case, we can consider that a small resistance or forward resistance exists in the P junction diode, so that this curve gets some slope. So this slope can be represented with this dotted line, form of slope. So 1 by RF. So because of this consideration of this slope, we can approximate this diode, which is equal to, a diode can be approximately modeled as a barrier potential V gamma and equivalent forward resistance, and with the ideal diode. You can consider ideal diode also, otherwise short circuit, which is in forward bias. So whereas in reverse bias, what happened from this 0 to negative potential? In the reverse bias of the P junction diode, absolutely the barrier potential or barrier junction will be increases, so that the resultant diode circuit act as a open circuit. So in this case, we can consider as open circuit in the reverse bias. If you take this approximation model to the P junction diode, same thing, take one network. network having a voltage, having resistor and a diode. By taking the third approximation, so replace this diode with a barrier potential. For silicon diode is 0.7 and the internal this resistance, forward resistance RF and a short circuit. So let us consider this voltage is 10 volts, okay, and then this one is 1 ohm resistor, external resistor, and then the internal forward resistance is, for example, 1 ohm resistor. So what will be the current flow in the network? So in order to replace this diode with this barrier voltage and forward resistance, so now we can analyze that what is the current flow in the induction diode in this network. So by applying the KVL law, so source voltage 10 volt, which is equal to the voltage drop across each element, algebraic sum of voltage drop across each element. Otherwise, algebraic sum of all voltage is equal to 0. So current I into R1 for example, plus 0.7 plus current I into RF. So when we take this voltage on one side, 10 minus 0.7, and take the I is common, and I R1 plus RF. By substituting this R1 and RF, then you can find I. Okay, I. So this you can find out I value. I is equal to 9.3 divided by 1 plus 1 ohm and nothing but 2 ohm. You will get the current flow in amperes or milliamperes. In this way, we can analyze by taking approximate model of this diode with the piecewise linear approximation and second approximation and an ideal diode approximation. Now coming to the load line analysis. What is load line analysis? In order to analyze a nonlinear network by using the load line analysis, this is one of the way to analyze the nonlinear device characteristics. So in graphical analysis of nonlinear electronic circuits, a load line is a line drawn on the characteristic curve or a graph of the current versus voltage in a nonlinear device like a diode or transistor. Simply we can say that load line is a line drawn on the characteristic curve. Here a line can be drawn on the characteristic curve of the device that represents the applied load. In the previous case, we can see that for example, there are these two loads, two resistors. We can consider those resistors as act as a load in the network. So here the line can be drawn with the help of those applied load on the characteristic graph. Then we can analyze what is the effect of that load in the network. The intersect point referring to as an operating point. In this case, here we can see that let us consider a diode connected to a resistor or a source voltage E in series. The diode is connected in forward bias so that the forward current flow in through this circuit. Then we can How can we apply the load line analysis? By taking the mathematical Kirchhoff voltage law to the series network, which consists of a voltage capital E and a resistor in series with this voltage R and a diode voltage. A diode circuit as shown in the figure. In this figure, a simple network, a series network of resistor and a diode. So with the external voltage E. So in this network, as I said, replace that diode with this sum of take any approximation. Let us consider that diode replaced with a diode cut voltage Vd, for example, and ignore that forward resistance in this case. So in order to analyze this one, take that diode approximation, and then we can apply the Kirchhoff voltage law to the network. So in order to analyze the load line analysis, first we can apply the Kirchhoff voltage law to the series network. Then what is the resultant Kirchhoff voltage law to the network? E capital E is equal to the voltage drop, the voltage barrier voltage across the diode. This diode replaced with the barrier voltage. For example, this diode replaced with the barrier voltage Vd, and then in series with the resistor. So in this case, so the right side diode voltage Vd plus current multiply with this resistor R, you will get the potential. So that source voltage, which is equal to the sum of the individual voltage drop across each element. So E is equal to Vd plus Id into R. The load line points can be determined from the above equation by substituting Id is equal to 0 in first case to get the point on the x-axis. Similarly, apply the diode voltage Vd is equal to 0 on the above equation, and get the point on the y-axis. So how can we get that point, load line point on the characteristic graph by considering this equation? This is the equation. This is the equation which can be derived from KVL law to the above network. E is equal to Vd, diode voltage, and current flow in the resistor I into R is nothing but VR. So I into R. This is the equation. And let us see first, if Id is equal to 0, then substitute this Id is equal to 0, this entire term gets 0. When this term gets 0, the resultant equation is equal to E is equal to Vd. What does it mean that V is equal to Vd? Nothing but on the x-axis, actually we have taken that a diode voltage Vd, and y-axis diode current Id. The diode voltage Vd, which is equal to supply voltage E capital E. So that is the point taken on the y-axis. And consider the second case. If Vd is equal to 0, then substitute Vd is equal to 0 in this equation. This is the equation for the series network. Equation 1. So in this case, if Vd is equal to 0, what happens? This term gets 0. When first term gets 0, the resultant equation E is equal to Id plus R1. Then what is the diode current? Capital ID is equal to capital E by capital R. This is the ratio. E by R is the another point on the characteristic graph. By taking these 2 points, if ID is equal to 0, VD is equal to E on the x-axis. If VD is equal to 0, ID is equal to E by R on the y-axis. So on joining these 2 points, we can get the load line on the characteristic graph of any nonlinear device. This is the resultant graph. So if you see that in this graph, take the x-axis diode voltage VD and consider this y-axis as diode current ID, and this blue color line which represents the characteristic graph for the PN junction diode VI characteristics, and this curve represents the current flow in the PN junction diode, and this characteristic curve derived from the device. Now how to place a Q points values on the characteristic graph. As I said, by considering the if ID is equal to 0, you will get VD value is equal to how much value VD? E, capital E. So on the x-axis graph, the value of VD is which is equal to E. For example, E is a 10 volt. So entire this graph, what is the E value is 10 volt. 10 volt. And another point, second case, if VD is equal to 0 in the equation 1, you will get ID is equal to E by R. So what is the value of E by R is nothing but some point on the y-axis. If you join these two, you will get the line. This line is called a load line to a particular network. For example, this is the network. So the cross section of this characteristic graph and a load line is called a Q point. Based on the Q point, so what is the significant behavior of that network? So by simply drawing a line down to the horizontal axis, the diode voltage VDQ can be determined as shown in the figure. Take the line. Similarly, whereas a horizontal line from a point of intersection to a vertical axis will provide a level of IDQ, horizontal line which is taken from the Q, which represent IDQ. So the point Q is nothing but IDQ, VDQ. We now have a load line defined by network and a characteristic curve defined by device. The result will be a change in slope of the load line and a different point of intersection between a load line and the device characteristics. What does it mean for different loads? Same network, if I am changing the load value. For example, in first case, I am considering 1 ohm. In second case, if I am considering 10 ohm. So in this case, if I am considering 10 ohms, so what happens? This will be changes. So E by this value is supply voltage is 10 volts. So what is the ID value? In the first case, 10 volt by 1 ohm, which is equal to 10 value on the 10 amperes. In the second case, 10 volt by 10 ohms, which is equal to 1 ampere. So for example, this is the 1 ampere. So then what happened? By changing the load, this Q point or this load line points also change. So then this line can be drawn like this for the second case. So what happened now? The cross intersection point of this characteristic graph and the second load line point will be 0. This is the Q point now. So by changing this value, by changing the load value, the load line value will be moved from this point to this point, so that the Q point will be changed. The resultant behavior of the network will be changed. So by taking this load line, we can also analyze the behavior of the network. So in this way, we can find out what is the here simply we can say that what is the diode equivalent circuit and what is the load line. The importance of diode equivalent circuit to analyze a network, and importance of the load line. So by taking the line drawn on the characteristic curve to find out the behavior of the network. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.